Hey everyone, Michael Unger here. It is a wonderful, beautiful day here on unceded territory of Musqueam, Squamish, and Tsleil-Waututh, which means that it is time for Ask an Astronomer with our very trusted, nerdy, wonderful astronomer, Marley Leacock. Hey Marley, how's it going?
Good. I like that your intro implies that we only do this when it's a nice day. Which is factually incorrect, but I like it anyway.
Okay, so I guess we have a 50% chance that on a Thursday at 4 p.m. we might be doing Ask an Astronomer, and then we have maybe what are you going to give like less than 10% that it might be a nice day for Ask an Astronomer?
Yeah. Yeah, probably. Because what nice days happen between May and well, they last longer and longer because of climate change now, maybe. But I guess into like October. By October, everything's kind of bad.
And then, of course, we have a very high percentage that will have maybe some geese that are going to be bugging us outside of our windows during this time because the geese are here. They're sort of like aliens, that come here. They're very strange looking. They look at us. They're like, "Why are you here? Why am I here?" But
They
this
know why
whole
they're here. They just don't want us around. They're very upset by the fact that we are in their way.
This is very true. And all month, because it is the month of May, we are delving into the science of science fiction. We got lots of fun events. We'll talk about some of those a little bit later. In fact, there's even a movie that's being set up in our lobby right now, Final Destination. I don't know if that's
No,
classified as science fiction. It's kind of fantastical fiction, maybe. How would
are
you
you allowed to
classify it?
tell people that that
Am
they're
I?
filming here? I don't know.
I don't know. Maybe I just let the cat out of the bag. But let's forget about Final Destination because let's talk about Dune because that is what this whole episode is dedicated towards. That wonderful David Lynch movie from 1983.
I believe you.
I guess we'll talk a little bit more about the Denis Villeneuve version, which I saw on opening weekend and I loved it. So if you are out there and want to get in on some questions, if you have any questions about Dune, the science of Dune, or perhaps any other questions under the universe, we're going to be here for the next half an hour, so you can ask any of those questions. So Marley, I assume that you've seen Dune. Have you seen all versions of Dune?
No. I've seen the most recent ones that were released while I was alive. Dune Part 1 and Dune Part 2. And I like them. I think they're fun. I love the worms. I wish I knew more about animal biology so I could talk about the worms. I love them. They're very cool.
Yes, the sandworms definitely look a lot better in the Denis Villeneuve version than the David Lynch version. But actually, I like all the versions. I'm a big fan of just the world, and I think that's one of the most intriguing things about this particular science fiction vehicle is that the worlds that are created are very, very specific and are rich with lots of things that connect to lots of worlds that we have found in our galaxy. So let's get into some of these worlds. But first, we have a very
Oh.
special update, or are you going to jump right into
No, we'll
Arrakis?
do the update. I wasn't sure if you were going to do the update. You were gearing up.
I was gearing up.
Yeah, you were gearing up.
But my favorite spacecraft, born the same year that I was born, thought it was dead, but no, I'm still here, as well as Voyager. What's happening with Voyager?
Yeah, so Voyager 1, this has been a very long journey with Voyager 1. In November of 2023, I think it was specifically November 14th, it stopped sending back readable science and engineering data back to Earth. So teams didn't know the health of the spacecraft, they didn't know the scientific information. It was like just a bunch of like garbled information. They could tell that the spacecraft could hear us and it was otherwise working normally, but any of like the health status science wasn't coming back properly. And so in this was like a long problem. They've been working on it for the past 5 months. And in March, the Voyager engineering team confirmed where the problem was coming from. They confirmed it was tied to one of three onboard computers, and those computers are called the Flight Data Subsystem. And the FDS is what like takes all the information, the science and engineering data, and packages it up and sends it back to Earth. And there was one single chip that was responsible for causing this catastrophic problem. And the single chip was responsible for storing part of the FDS memory. And that one chip just wasn't working. And so without that chip, it meant that the science and engineering data was completely unusable. Like it wasn't able to be stored and packaged and like sent back to Earth. Like it was gone. And we can't go out there and fix the chip. This thing is really far away, like in the billions of kilometers far away. So what they had to do was find a workaround. Like, how are we going to fix the programming on this thing that it takes 22 and a half hours to send a signal out? How are we going to fix it so that we can hear from the spacecraft again? Um, so what the team decided to do was place the affected code somewhere else in the memory of the subsystem. No single spot had enough room to hold a complete section of code that was causing the problem. So they divided the code into different boxes, like split it up, and stored those boxes in different rooms in the FDS. That's the best way I can explain it, because otherwise this is weird. Um, but they also needed to make sure to adjust the sections of code that reference this broken part. If they were referenced somewhere else in the programming, and it, like, say, for example, it said, look in room X for this, and they moved that object to room Y, they had to update it so the code said, look in room Y, because it would look in room X, not find anything, and then you'd have more problems. So they had to basically update a lot of the programming on Voyager 1. And they sent that code to the new location with all the new instructions on April 18th. The radio signal takes 22 and a half hours to reach Voyager 1. It's 24 billion kilometers away.
Wow.
It takes another 22 and a half hours to get back. So basically, you're waiting 2 days, right, to figure out if it's worked. The modification did work, and the team heard back on April 20th. And that was the first time they were able to check the health of the spacecraft since it went down on November 14th. And this is a picture of the team, or parts of the team, when they heard that back on April 20th at 6:40 a.m. was when they got the signal back. And as you can tell, they're really, really happy. I'm this guy back here. Like, that's awesome. That is, yeah, very celebratory. So this is great. I don't know, like, it's a really huge feat to be able to fix something that far away and wait that long. And the fact it's like still working, and we can still fix it, and we can still get valuable information from the spacecraft, because the farther away it is in interstellar space, the more we learn about that environment that it's very difficult to study. And so it's just awesome. I'm very happy for them and happy the
Absolutely.
spacecraft's working.
Yeah, absolutely. As long as there is any Voyager news, we will always feature it here. Of course, my very favorite and beloved mission. But let's get to our main story for this episode, which is the science of Dune. And as we talked off the top, some of the world building, some of the worlds are very specific, and we can compare them to some in our galaxy. So let's start with Arrakis. Marley, how can we think about Arrakis in our own universe?
So Arrakis is very interesting because it's bone dry, right? Like, that's kind of the whole problem,
It's
right?
the
There,
whole, it's called
it's
Dune.
called Dune. Yeah. Love that. Very astronomical of them to name it after what it does. But it's, it does have some water, but it's mostly underground reservoirs or deep in the planet's interior. You see, in the film, there's like these large sand dunes. I guess there's also rocky outcrops and salt flats as well across the planet. But we know that it's suitable for life because life manages to exist there. They're just very extreme forms or extremophiles types of life. But I did find there's so much about this world. Like, people get really anyway. There's like, it apparently has a mostly nitrogen and oxygen atmosphere, very similar to Earth's atmosphere. So it's breathable, right? We see when they're out on the surface, they don't wear any special suits except for the Harkonnens do, because that's pretty cool. But they don't have any special suits or anything like that. They're able to just breathe the air, even though you might not want to. And there's also some vegetation and animals, like the little mouse, right? So, and of course, the worms, the best part.
Mhm.
But I also found in reading about Arrakis that it orbits a star, and the star is named. And the name of that star is Canopus. Now, Canopus is
Mm.
an actual star that we can see in the southern sky. It's a star visible from Earth. And also, Arrakis has 2 moons, I found out, which I thought was very cool. Um, will those ever come into play? I don't know. There's a lot of books about this place, but it's still pretty cool. So what interested me most of all was the fact that there's an actual star
Mhm.
that this planet orbits. So Canopus is not a star we can see from the northern hemisphere. This is for our friends in the southern hemisphere, because it's in the constellation Carina, which we don't see up here. It's this star circled in red in this star map here is the star Canopus. Unfortunately, we never see it. It's scientific name, I guess you could say, is Alpha Carinae, because it's the brightest star in the Carina constellation, and it's 313 light years from Earth. So this star is within our Milky Way. Is it? No, I can't remember. It's close, right? We could feasibly not get there, but we can study it now.
Hmm.
Now, Canopus, the star, is not like our sun. It's the second brightest star in our sky. It's only outshone by Sirius, so it's a pretty bright star. You can actually see Sirius and Canopus at the same time in the southern hemisphere. It's what we call an A9 bright giant. And what that means is that its spectrum, so the light that we get from the star, is mostly just absorption lines on a visible continuum, but there's some emission lines detected, but they're usually typically quite weak. And that just might be due to different areas on the stellar surface, whether they're active or changing. It's essentially white when we see it with the naked eye, and its luminosity is over 10,000 times that of the sun. So it's an exceptionally bright star. It's also very massive. So it has moved off of the main sequence, and it's now burning helium in its core instead of hydrogen. So our star is on the main sequence. It is burning hydrogen into helium. This star, as an A9 bright giant, is now burning helium into the next available element. And it's currently stuck in what we call its blue loop phase, which means that it's already turned into a red giant and now it's turned into a blue giant. And that can just like happen in a cycle over and over for a while until the star either dies or evolves into something else. It's also a source of X-rays. So that's bad when it comes to life on surrounding worlds, right? That makes it very fine. Like our sun also does that, but like we have an
Yeah.
atmosphere and stuff and it's not as intense. This is pretty bad. But what I wanted to find out once I figured out that this was an actual star, which you can see, oh no, come back. And that's the star there in this picture, the very bright one.
Nice.
I wanted to figure out what's the habitable zone of this star. Like
Yeah.
where could if Arrakis had liquid water on the surface, it doesn't, but hey, where's possible? So the habitable zone, for those of us who don't know, is the distance from a star at which liquid water could exist on orbiting planet surfaces, or basically just a range of orbits where liquid water could be on the surface of a planet. This is kind of how we define a habitable zone based on water, because that's how we understand life needs to survive. We understand that it needs water for a variety of reasons. So I thought, why not apply it to this? Because the whole problem is there's no water. So these numbers are all for the sun. So for our sun, the inner limit of the habitable zone is about 0.95 astronomical units, and the outer limit is 1.4 astronomical units. For reference, the Earth sits right at 1. So the Earth is 1 astronomical unit away from the sun. It's right in almost the middle of that happy little area, right? With a bit on either side. The closer you get to the star, the more heat you'll receive, the more radiation you'll receive. And so water will either be in vapor or not on the planet at all. And the further away you are, the colder it is, the less radiation, the less heat you get. And so water freezes, right? So Mars and Venus in our solar system, Mars is in this red band, right?
Mhm.
No water. And then, or Venus is on the red band, no water. And then Mars is kind of on the outskirts here, right? Right on the blue green edge. And
Yeah.
it has water, but it's not liquid. It's all frozen in ice caps. So what about Canopus, right? What if we apply this to Canopus? And so I involved math because you have to. But I got really into the math, so you guys didn't have to. So this was taken from planetarybiology.com. This professor, I think his name was Tom Morris, had a whole rundown of how you can calculate habitable zones around different stars. And what's interesting is that this does not have an exception for planetary mass. There is another method you can do, but it has to be done with a main sequence star, which Canopus is not, and also takes into account the planetary mass of the world you're working with, which it was too much math, and we wouldn't have time for me to do it all. But basically, there's a lot of math here. Don't worry about it. We have to start and find the inner radius, which is Ri, and the outer radius, right? So that is like our range. And basically what it comes down to is taking the square root of the luminosity, or kind of the brightness of the star over a specific value. And that specific value is calculated based on a bunch of stuff. The luminosity of the star is taken in terms of solar luminosities, which is a really easy way for astronomers to understand what we're talking about because we have a pretty good understanding of how bright the sun is, but also so we don't have to write down a lot of numbers because this gets really big.
Right.
So Canopus has a luminosity of about 10,700 solar luminosities based on one calculation. There's other ways to get it. And so we find our inner and outer ranges to be 98.6 AU for the inner limit, so about 99, and then 142 AU or about 140 astronomical units. So the range at which Arrakis could sit if it had liquid water on its surface could be in between those two. When you take into account planetary mass, this is like where it gets kind of fun because Arrakis has this atmosphere, but apparently it's about only it's the size of our moon. It's a quarter the
Hmm.
size of Earth, and that's not big enough to hold on to an atmosphere,
Yeah.
and so it has to be really dense. So I guess this planet is just mostly metal, which is cool. Um, because it doesn't have the liquid water on its surface, because it's so hot, it has like these extremely hot days and like relatively okay nights. It's probably closer to this in this reddish zone somewhere. And perhaps when it was, you know, nicer, it had an atmosphere more sustainable, it had different life forms. I don't know how much I'm allowed to spoil, but apparently it was like terraformed and stuff. Like it was not always like this, right? It was
Okay.
not always like this. Very similar
I don't
to
know if that's a spoiler. I think that's a deep
okay.
dive. That's a deep cut.
Okay, yeah, because I got really into the Dune wiki for a couple days and I forget what's known and what's not known. Those people are cool. They know so much and wow, it's really well done. But it reminded me a lot of Mars, right? So basically, this planet Arrakis that is on kind of this edge of probably being in a habitable zone or not. At one point, may have had liquid water, the same as Mars did, may have had more lush vegetation. Jury's out on whether or not Mars did or not. We are convinced that it had some liquid water on the surface, and now it doesn't. Which made me think about, how much of Mars inspired the world of Arrakis, right? Like back in the 1960s, we didn't know everything about Mars that we do now, right? So
Hmm.
obviously a lot of that has changed. But I don't know, it was just still very interesting because Arrakis is also like geologically active. Which Mars is pretty quiet, but Venus isn't. Venus has a very geologically active surface, which we only know now, with
Yeah.
confirmation, I think in March of 2023, that there were active volcanoes on Venus. So Arrakis seems to be this mixture of some elements of Mars, some elements of Earth, and then also some elements of Venus. But a lot of it is stuff that we've only discovered recently, which I thought was
Yeah.
pretty neat.
Yeah, and that's interesting because back then, even before the 1970s, Venus was thought of as being a potential habitable world. Now we don't. So, going back to the habitable zone, if let's say Venus didn't have those thick cloud cover, and just looking at the ability to have liquid water at surface, given its distance from the star, could Venus have liquid water?
I don't know for sure. I don't know exactly what its AU distance is because I don't. Oh, of course, if you look it up, it gives it to you in kilometers, which is unhelpful. Um,
And then I guess like the flip side to
oh, oh,
that
oh,
would
oh.
be
0.72. So it's just so if I go back to the sun's option instead of Canopus's option,
yeah.
Venus sits, kind of pretty far in there. So probably not, even if it didn't have those
Okay.
clouds and stuff, probably not. There's like water vapor on Venus. It's just all vapor.
Yeah. And then I guess the flip side to that would be if Mars was maybe a slightly bigger planet, had a thicker atmosphere, would it actually be warm enough to actually be a habitable planet that would
Yeah,
have liquid water on its surface?
that's what we think had happened to Mars. At one point, it had an atmosphere thick enough to sustain liquid water on the surface
Mm,
because all of the evidence we have from Curiosity rovers and past rovers tells us that, with pretty confident that there was water, liquid water on the surface of Mars. Like it has those rounded pebbles that you could only get through erosion. It has clays that are only formed in the presence of water, of liquid water. So it had to have been there. It's just what conditions were around to make that possible. And one of the easiest answers is that it had a thicker atmosphere, able to hold that water in and keep the planet warmer.
Yeah. Awesome. All right. So if you're out there watching, want to get in any discussion about Arrakis, get into the chats. We've got about 9 more minutes for this show. So Marley, I think let's go leave Arrakis behind. Well, actually, we're going to stay on Arrakis and thinking about the Fremen and how they are able to retain their water. And this
Yeah.
and this is a really intriguing thing that we actually talk a lot about when it comes to the International Space Station. But let's just talk about, how valuable water is and thinking about sustainability for, a biological life form that needs water on a world that is a very dry place. So let's talk about the Fremen and how they're able to do that.
So the Fremen have the still suits, I think is what they're called.
Hmm.
And they are a full suit that they wear, body fluid recycling suit, right? So all of the fluid that comes out of their bodies gets recycled, that they're able to drink and maintain. And they're very, very advanced. I think they say they only lose like a thimbleful of water each day, like from their bodies, which is pretty cool because your bodies are actually losing a lot of water continuously. So you lose it from breathing every time you exhale.
Hmm.
It's not just carbon dioxide, it's actually also oxygen and water vapor and a bunch of other stuff. Sweating, even just like existing, water evaporates from your skin to keep your body temperature cool. And of course, waste, right? So, waste is where we lose most of the water. I think for urine, it's anywhere between half to 10 liters are lost a day, depending on your bodily functions and what you need and what's going on. But also, you can have problems from like vigorous exercise, hot weather, or high body temperature can all contribute to more water loss as your body tries to keep itself cool and keep itself from overheating. So this is a huge problem, especially if we are hoping to explore Mars. We can't pack up all the water with us. It's a bad idea. And so we have to figure out a way to be like the Fremen and hold on to the water that we have and recycle it. And this was a problem that was encountered in the International Space Station. So at the ISS, it recycles water from all of these areas, from urine, moisture from exhalation, sweat, showering, shaving. All of the water from those activities is ran through a very intense filtration and cleaning system and recycled throughout the station. So that's what ends up being their drinking water. And the station that does this is the Environmental Control and Life Support System. And this is an image from 2001 of the ECLSS of the ground copy. So there's always two of everything. There's one installed on the space station, there's one on the ground, there's probably more copies somewhere else, but they always have one on hand because if something goes wrong, they can workshop it on the ground. And so, how the ECLSS works is that it's a combination of different hardware, including a water recovery system. It also does oxygen and breathing air, but we're going to focus on the water part. So, the system collects the wastewater and sends it to the the water processor assembly or the WPA. It gets cleaned. Some of it becomes drinkable water at that stage. There's another specialized component, uses very, very advanced dehumidifiers that actually capture the moisture into the cabin and breath and sweat and cleans them, sends them to the WPA and has it cleaned. The urine processor assembly, or the UPA, is another subsystem that recovers water from urine, like from the toilets on the space station, using vacuum distillation, which is cool. And that produces water and what's called a urine brine, which sounds horrible. There's still reclaimable water in the urine brine. And up until this point, that was kind of the end, right? They got it all the way down to water and urine brine, and that was the water recovery amount of 93 to 94%. So any water that was put out into the ISS, they were able to recover 93 to 94% of it for drinking and hygiene uses.
Nice. And that was
They
actually a question that someone just asked about
Ooh,
on Instagram, Sylvester Law. What was the percentage of water can they recycle, and how important is that going to be for a long, deep space mission?
very to the point where 93 to 94% was not enough. They wanted to get that higher. And so, because there was still reclaimable water in the urine brine, they added the brine processor assembly, or the BPA, which extracts the remaining wastewater from the urine brine. It runs it through a special membrane technology and then blows warm, dry air over the brine to evaporate out all the water and leave like the salt. And that humid air is collected by the station's water collection systems, where it re-enters the WPA and gets re-cleaned and sorted through. And that got them up to a 98% total water recovery, which is
Nice.
like, it's pretty good. Um, it's amazing, honestly. All the water is treated by the WPA, so that has specialized filters, catalytic reactions, breaking down any contaminants that are still there. Sensors are built in that check the water for purity, and unacceptable water is reprocessed until it's at a suitable level. And the system also will add iodine to acceptable water to prevent microbial growth and stores it until the crew uses it. Because each crew member uses about 4 liters of water a day for
Hmm.
consumption, food, because everything's dehydrated, you have to add water to it, um, hygiene, like brushing your teeth. And while it sounds like really gross, the water up there is actually cleaner and held to a very stringent standard, to the point where it's cleaner than the water that we drink on Earth, like every day. Like it is incredibly clean up there.
And yet you have
Um,
said multiple occasions that you will not go up there because you
no,
don't want to be drinking filtered pee.
no, I really don't. I can't. It's the mental block. I just can't get past it. I really can't. Like, I guess like if you just don't think about it, it's probably cool. Those
Yeah.
people are, they're just, astronauts are always so interesting people that I guess it's just not a problem for them. Or maybe it's a me issue, but it's still pretty cool.
Amazing.
Yeah.
And of course, like the as was asked on Instagram, this of course is very essential for deep space travel. But even just thinking about going to Mars, I hadn't even thought about the possibility that they might be able to do this in their suits as well.
Yeah. Well, they had to for Apollo, right? Like this has been a really long problem. So this is a picture in the background of NASA astronaut um, Chris Cassidy conducting a spacewalk, right? So those can take 6 hours, 8 hours. Like that's your whole day is in that suit out in space. And so a question was, what about all the water that's being produced in those suits? Because while we can move the water on the ISS, that's not the same necessarily as being in a still suit like the Fremen, right? We're not on the surface. So what about when we're on the surface? Well, there's a couple things that happen. There's the liquid cooling and ventilation garment, the LCVG, which is what this gentleman is wearing down here. I think it's so funny. It has clear plastic tubing and chilled liquid water flows through it for body temperature control. So the first idea in the way of conserving water is just stay cool enough that you don't sweat excessively, so you don't lose too much water than you need to. But the liquid water also helps to move around waste gas removal and ventilation as well. Water goes through the tubes, removing heat from the body, resulting in a lower core temperature, and the water returns to the primary life support system, which is the big backpack that they wear, right? So in their emu suits, they wear these big backpacks, and inside that backpack is the primary life support system. And it has a bunch of jobs, but its main job is to remove carbon dioxide, odors, contaminants, and humidity from breathing O2 or from breathing oxygen. It's not its main job, but for the purposes of today, kind of what we're going to focus on.
Hmm.
So, oxygen and carbon dioxide and water vapor are taken away from the suit extremities by these cooling tubes. The cooling tube sends the gas to the PLSS, that act inside the PLSS, there's activated charcoal to remove the odors. There's lithium hydroxide to remove the carbon dioxide, and a sublimator to condense water vapor, which is then removed by a slurper, whatever that is. I think that's hilarious.
It sounds very science fiction, a slurper.
Yep. And that removed water then goes back into the LCVG tubes to help keep the body cool. So they don't use it for drinking. They have special drinking pouches that they use. In the event that they have to use the washroom, they're wearing a diaper or a maximum absorbency garment. But I read that astronauts will actually time their drinking so they don't have to use the diaper, which I thought was Yeah, same. Absolutely. So it's pretty cool. So really to get a still suit like the Fremen have, what we would need to do is somehow combine the tubing of this primary life support system with all of the filtration we have on board the International Space Station, which I thought was pretty awesome.
Amazing. Well, we're winning a little bit over time, but that's okay because we got a few more quick questions
Oops,
you could
that's not our phone number.
um that you can maybe answer, or maybe we'll look up for next show. But do you know the approximate cost per kilogram to bring things like water or anything like that to the ISS and the moon?
It depends who's sending it, I think.
Okay.
Because different spaceships will have different fuel requirements. I don't know off the
Yeah.
top of my head. I read there was one that they're developing. I can't remember what company it is, but it was like $50,000 per kilogram. I think it was for a lunar project. So it can get quite expensive.
Keith also mentions that Singapore has been recycling wastewater for consumption for about a couple decades. It's known as new water. I didn't know that.
Shout
That's
out
pretty cool.
Singapore.
So Maya asks, could they break the CO2 to get O2?
Oh, yes, they could. So that's what Moxie did on Mars. So the Perseverance rover carried an experiment called Moxie, which took the atmospheric air on Mars, which is mostly carbon dioxide, and ran it through a bunch of complicated engineering stuff, a lot of like electricity, which broke it into carbon and breathable oxygen. So yes, that's also something they have done. They have tested it. Moxie was the tech demo for that.
Awesome. And last question from Keith, going back to the habitable zone questions. Is there a simulation astronomy software where you can adjust star type and star size so you could analyze the habitable zone and kind of play around?
There is it's not like it'll just give you numbers. And I can put that into the chat. I just have to find out where actually I can't put it into the chat. I can
I can put it in the chat if you
oh,
put it
Michael
into the
can put
chat.
it. Oh, well, let's see if my computer lets me do it. No, it was okay, I'm gonna stop sharing and then I'll be able to get to it and then I'll put it in the chat for Michael and then he can send it to Keith. But yes, it's like it doesn't let you change the star. It lets you change, well, it doesn't let you it lets you change the temperature of the star and gives you different sizes for I don't want to share my screen for planets.
Hmm.
But it there we go. There's the one where you can play around. If it will, there it goes. That's the one that yeah, it only will take like a main sequence star, but you can play around with the effective temperatures and stuff like that of different stars that you may know of. And then the one that I used that did not have anything about main sequence stars, it was just for whichever I'll send to Michael here. That was the planetary biology one, is the one that I used for this presentation.
Awesome. Well, thank you, Marley. This was amazing and fulfilled all of my nerdy dreams to get into the science of Dune. We're going to have two more episodes this month. So May 16th, May 30th, we're going to be continuing on with our series on science of science fiction. So if you want to get in on any science fiction vehicle that you love out there, want to know more about the science of, you can send us some questions. You can either send in through us on our social media accounts on Facebook, on Instagram, or send it via email, info@spacecenter.ca. And of course, we're focusing in on one particular science fiction vehicle that Marley and I both love, and that is Star Wars on Saturday, but tickets are almost sold out. So if you are out there watching and you want to get in on this event, which is going to feature violist Thomas Beckman, and as well as another musician, they're going to be playing a selection of tunes live in our planetarium, as well as the 501 Legion. We're going to be here in full costume, so you can take pictures with your favorite stormtrooper. Darth Vader is probably going to show up. Last year, we had a fully functional R2D2 that was driving around, which was amazing because R2 is my favorite character
I'm still
in
holding
the
out for
Star.
Darth Maul. I'm holding out for Darth Maul.
All right, I'll send a message over to the 501.
Thank you.
So thank you all for joining us for another edition of Ask an Astronomer. Like I said, we'll be right here in 2 weeks for another episode. We'll see you all then.